We see it pretty much every night, that familiar, silvery face up in the dark. But how often do you really stop and think about why it changes? Well, today, we're going to dive into how the moon's shifting face does way more than just light up our sky. It actually sets the rhythm of our lives.
So let's set the scene. Picture this, a kite festival. A young girl, Mira, is there, watching her kite dance against this beautiful sunset. And then she spots something else up there, this pale, silvery sliver. It's the moon, but it's still daytime. And seeing that just got her brain spinning.
I mean, it's a simple question, right? And I'm willing to bet most of you have. But have you ever really, truly paused and wondered why? Why is it sometimes just hanging out in the blue sky? And more importantly, why does it change its shape every single night? Well, Mira did. And her simple questions, they lead to some pretty amazing answers we're going to unpack.
Okay, so let's start with that first puzzle, seeing the moon when the sun is still out. What exactly was going through Mira's mind?
Well, Mira knew a few basic things. One, the moon is a sphere, a giant ball floating in space. Two, it doesn't have its own flashlight. It just shines by reflecting the sun's light. So, wait a minute. If that's true, shouldn't we see a full, bright circle every single night? For a split second, she thought, is it an eclipse? But no, that didn't feel right. Eclipses are these huge, rare, dramatic events. This was happening all the time. Something else had to be going on. To really get to the bottom of Mira's mystery, we first need to get our vocabulary straight. What do we call these changing shapes she was seeing? Well, they're known as the phases of the moon. And here we're looking at the whole cycle. So when we say phases of the moon, all that really means is the different amounts of the sunlit side that we can happen to see from down here on Earth. The moon itself isn't actually changing shape, not at all. It's just that our view of its bright side changes night after night over the course of about a month. Now, this whole cycle is basically split into two halves. First, you have the waxing period. That's when the bright part you can see is getting bigger and bigger each night. And then, once it hits full moon, it starts the waning period, where the light begins to shrink away again. And during these two periods, we see all those shapes we know and love. It kicks off with the new moon, where, poof, it's basically invisible. Then you get that beautiful little sliver, a crescent, which grows into what we call a gibbous shape. That's just a fancy word for more than half lit, all the way up to that big, brilliant full moon. And then the whole process just goes in reverse. Okay, so now we know what to call it, but we still haven't answered the big question. Why does it happen? Let's get to the real science behind it all. This is the cool part. Now, I want you to be honest. What's the most common explanation you've ever heard for the moon's phases? I bet it's this one, that the phases are caused by the Earth's shadow falling on the moon. I mean, it sounds logical. It makes a certain kind of sense, but is it actually true? No. A big, resounding absolutely not. In fact, this is probably one of the single biggest misconceptions in all of astronomy. So here's the deal. The Earth's shadow falling on the moon is a real thing, but it's got a different name. A lunar eclipse. That's a totally different phenomenon, and it only happens on rare occasions when the sun, Earth, and moon line up perfectly. The daily phases we see, that's caused by something way more routine. The real reason is all about your point of view. And here's a super simple analogy you can try at home. Go into a dark room, get a lamp, and pretend that's the sun. Your head, you're the Earth. Now, grab a ball. Any ball will do, and hold it out at arm's length. That's your moon. Now, as you're holding that ball, just slowly turn yourself in a circle, keep your eye on the ball, and watch how the light from the sun lamp hits it. From your perspective, from Earth, the amount of the lit up side you can see is changing. You're creating phases right there in your room. And that little experiment is exactly what's happening up in space. The moon is always half lit by the sun, always. But because it's orbiting us, our viewing angle of that lit up half is constantly changing. Sometimes we see the whole bright side, sometimes just a sliver, and sometimes none at all. So remember, the key takeaway is it's not a shadow, it's just our perspective. So Mira's question is solved. It's all about perspective. But this predictable cycle of phases isn't just a pretty thing to look at. For thousands of years, humans realized this reliable cosmic dance could be used for something incredibly practical, keeping time. It all starts with the most fundamental rhythm there is, the day. And that's simply the time it takes for our planet to do one full spin on its axis, which we measure by the sun's journey across our sky. Simple enough. So what's the next unit of time up from that? The month. And where does that come from? You guessed it, it's the time it takes for the moon to go through one full cycle of its phases, from one new moon all the way to the next.
And finally, we've got the big one, the year. And that is the time it takes for our planet Earth to make one full trip, one whole revolution, all the way around the sun, which of course brings with it the changing of the seasons. Now, just let that sink in for a second. The Earth's spin gives us the day, the moon's orbit gives us the month, and the Earth's orbit around the sun gives us the year. Our entire concept of time isn't really an invention, it's an observation. We built it by watching the steady, predictable ticking of these three giant celestial clocks. But, as you might have guessed, there's a problem. A really big one, actually. These three cosmic clocks, they don't tick in perfect harmony with each other. So, ancient cultures basically had to pick a clock to follow. A lot of them went with a lunar year, which is based on 12 full cycles of the moon, because it's super easy to see. Others, especially those focused on farming, used a solar year based on the cycle of the seasons.
Here's the catch. Those two systems don't line up. If you build your calendar strictly on the moon, your months will slowly drift out of sync with the seasons. Pretty soon, your big summer harvest festival would end up happening in the middle of winter. That's a problem.
And here's the cold hard math. 12 trips of the moon around the Earth add up to about 354 days. But one full trip around the sun, a solar year, takes about 365.25 days. So you've got this pesky mismatch of about 11 days every single year. And hey, this isn't some modern discovery. Ancient Indian texts like the Taittiriya Samhita show these incredibly detailed observations of the sun's path. They noted its 6-month journey north and its 6-month journey south. People have been wrestling with this cosmic math for thousands of years. So how did we solve it? Specifically, what do we do about that annoying quarter of a day that messes everything up? Well, the solution is this ingenious little hack that you know very well, the leap year. By just adding one extra day every 4 years, we basically hit a cosmic reset button, pulling our calendar perfectly back in line with the seasons. So the next time you look up and see a crescent moon in the daylight, just like Mira did, I want you to remember this incredible story. A story that connects a child's simple question all the way to why we have a February 29th on our calendars. It's just a powerful reminder that our daily lives are shaped by this grand cosmic dance, and that we are all, quite literally, keeping time with